All right, let's start. So today we're back to covering some new content that's in many ways complementary to what you're doing on the MP. You'll see the appearance of a data structure today that we expect you to use on the MP. So the kind of plan going forward for the remainder of the semester, the time we have together, is to do two kind of new things. One is we're going to start to look at a series of data structures and get a sense of, some of their, we'll implement some of them together. So next couple lessons, you guys will be doing, building a couple of different type of lists. And then we'll also start analyzing algorithms and analyzing data structure performance. So as we build these data structures, from time to time, there's some new pieces of Java syntax that we'll have to introduce. So we will. There's one today already. And so we'll do that as needed. But our main focus is not, at this point, on introducing new syntax. It's more on, covering some new concepts. So our warm-up kind of is lists. Lists are quite similar to arrays in many ways, and so they're a good starting point. We'll do that for the remainder of the week, and then we'll move on from there. But as we go, we're going to be stopping more often to kind of say, okay, this particular operation on a list, how long does it take? And we'll continue to practice that as we go. So the main one of the things we do today is we introduce some new sort of vocabulary for discussing how things perform that we're going to be using throughout the remainder of the class. So when we analyze algorithms, we're normally interested in some aspect of their performance. For example, how long does it take to run? The time it takes something to run turns out to be pretty important. I mean, computers are quite fast, but when you're working on large problems, the time it takes for something to complete can start to become an issue. And so we're also going to develop some vocabulary for talking about how long certain things take. And usually in computer science, when we talk about how long something takes, we don't talk about it in absolute terms. We don't say, oh, it takes 10 seconds or whatever. Because usually the amount of time something takes is dependent on the size of the problem. So for example, if I needed to sum all the elements in a list, well, summing 10 elements might be quite quick, but summing a larger number of elements, like 100 elements or 1,000 elements or 10,000 elements or 100,000 elements or 1,000,000 elements, starts to get slower and slower and slower. And what we're interested in is the relationship between the size of the problem, which we measure in different ways depending on the problem that we're looking at, and how long something takes. And so in this lesson and some of the videos, we go through looking at these sort of different categories. And the categories that we use in this class have to do with the relationship between the size of the problem and how long the algorithm is going to take to run. Typically, we represent the size of the problem as n, and then we have different O of n categories. So we say something is performance is O of n if its performance is linearly related to the size of the problem. So for example, if I give you a list with 10 items and it takes a certain amount of time, if I give you a list with 100 items, it takes roughly 10 times longer. That's O of n. We also have cases where we see the performance increase as the square of the number of elements. So if I give you a list with 10 items and it takes a certain amount of time, and then I double the size of the list, it takes 4 times as long. If I triple the size of the list, it takes 9 times as long. So if I make the list 10 times larger, it takes 100 times longer. So now the amount of time it's taking is not growing linearly with the size of the list. It's actually growing exponentially. And there's a couple of other categories here too. That's as detailed as we're going to get in this class when we talk about big O analysis. When you guys go and take future CS courses, they'll go into more detail about this and you'll come up with more accurate formulations of exactly how long certain problems take. But for our purposes, the goal here is to develop intuition about certain problems and why they take a certain amount of time, right? One of the things we'll do, and actually maybe I'll do this here because this is my chance to have some fun. As always, I'm happy to take questions. We'll look at lists in a minute. That's another thing that we bring into today's lesson. So is how do we measure how long stuff takes? So maybe we can do that for fun. Let me take over this little playground here and try to remember how to do this. I think there's a function called system.get current time millis. Does that work? Maybe it's just current time millis. There it is. Okay. And you'll see if I run this a bunch of times, what's being displayed here is the current time in milliseconds. If I took this and plugged it into some sort of millisecond to current time converter, what you'd find is this should correspond roughly to the current time. And so we can use this to measure how long certain things take. Now here's the problem. Let's see here actually. Java time nanoseconds. Can I actually get system nanotime? Ooh, okay. That's cool. Let's try that. Nano time. Wow. Awesome. Okay, so we can actually even get nanoseconds. That's going to be useful because some of the things are the playground examples that we allow you guys to run, the time that they execute for is limited, if I remember correctly, to 100 milliseconds. So some milliseconds isn't really quite precise enough, but the fact that we can use nanoseconds is kind of cool. So let's try this. Let's take an example. What I'll do is I'll just create a random array. Let's do this. So we'll say random values equal to new int, and for starters I'll make this 1024. And then what I'm going to do is I'm going to go through this and I'm going to fill it. I'll import java.util.random. And now what I'll do is I'll fill this with random integers. So I'll say for int I is equal to 0, I is less than random values dot length I plus plus. I'll say random values I is equal to new random. Sorry, I need an instance of my random thing. So I'll say random to create a new random number generator, and I'll say random.next int. And just for fun, I'll actually give it a bound of 32, just so these don't get too big and the sum doesn't get too big. Okay, looks like it's upset about something. I don't know why. Let's see here. I think I have some sort of syntax here. Here that I'm having a hard time. Okay. Okay, that works. No, it doesn't like this. Okay. Try something else here. All right. Sure what's going on here. I'm going to put a call to this down here. And now, yeah, clearly I have a bug in this. Oh, there it is. Man, Professor can't write code. It's early. All right, there we go. So now let's see if we can capture how long this is actually taking. So what I'm going to do is I'm going to say long start is equal to system.nano time. That'll give me the time when things get started. And then I'm going to say for int I is 0, I is less than random. Now we'll do a sum. Random values dot length I plus plus sum plus equals random values I, and then I'll say long end is equal to system dot nano time, and then I'm going to do is I'm going to print the difference between these two. That will give me roughly how long things took. And you can see if I run this, the numbers are they're going to bounce around a little bit. This is actually a real wall clock time, and so this is not necessarily going to be super consistent, but it's actually not too bad. This is taking about 22 milliseconds. Okay, let's try making this longer and see what happens. Okay, so and you can see actually it's kind of a nice description. Sorry, this is not 32 milliseconds. Actually 32 microseconds. These are nanoseconds, right? So this is pretty fast. And you can see it's kind of taking a relatively consistent amount of time. It's about 22 microseconds. And if I make, so we talked about, this algorithm is O of n. This algorithm performing the sum, you may not even think of it as an algorithm, but it is. I mean, this is how we do a sum. It's a simple algorithm and one that you're familiar with at this point, but this is how we do it. So, and you'll see that it's taking, about 22 milliseconds each time, 22 microseconds. If I make this 10 times longer, now it's taking about 10 times as long. If I make this 10 times longer again, now it's taking about 10 times as long. So this algorithm the amount of time that it's taking is scaling with the size of the problem. The problem gets 10 times bigger, takes about 10 times longer, right? And so we can measure this empirically. That's what we're doing here, right? But usually when we talk about this as computer scientists, we don't, like I said, we don't talk about the numbers. We talk about this relationship that's being established here, right? Because the relationship is what allows me to think about how this would affect my code, right? So let's say I'm writing some tests, I'm writing some app, and I'm thinking, okay, and again, you can think about this from the perspective of the MP that you're working on, right? Sorting. So the comparator function that you guys are writing is used to sort that list of courses. We'll talk about sorting algorithms in a minute. The filter function that you guys are writing to go through the list of courses, that has to go through every course. That function is O of n. Currently, we're giving you a list of 62 course summaries. That's only for the computer science department. If we did every department at the university, you'd have a list that would have several thousand in it. So if you thought about the filter function that you're writing, for example, that function is going to be O of n. It's going to take longer and longer, proportional to the length of the list, for that function to run. So at some point, now, when things are really fast, you don't notice. There are limits to our human abilities to perceive how much time something takes. So if something is so fast that you don't notice, making it 10 times slower, that doesn't always mean that it's slow enough that you start to notice. But at some point, if we fed more and more and more and more courses into that view, it would start to matter. And you'd actually see it start to slow down, and you'd have to think a little bit. It might freeze for a second while it was running, and we'd have to go ahead and do something about it. That filter function is O of n. The sorting function is not O of n. We'll come back and talk about that. We are going to spend some time later in the semester implementing and analyzing sorting algorithms, and they typically have you can't sort in O of n. The best you can do is O and log n, and we'll talk about why that is. Okay. Any questions about this so far? I don't want to sort of go and do a reprise of all the lesson content as usual, so I'd rather take some queries. The other thing that we're doing today is that we're starting to work with lists in Java. So some of you are probably thinking, like, finally, on Python I can use a list on day one, and that's true. One of the reasons why we don't have you work with lists right away in Java is because of this aspect of type parameters, which we also go into today. But Java does have a list. That's part of, it's not built in, so it's not quite as easy to use in Python. In Python, the list is just there, ready for you to use. It has its own syntax. You put things in square brackets, you got one. In Java, our list is a Java class, right? There's something that implements a list. And then there's also a list interface. And so in order to use a list, we're going to have to use both. So the interface is java.util.list. Now, this is a cool example of the use of interfaces because there are a number of different ways to implement a list. We're actually going to do a couple of them together over the next few days. And so the list interface in Java defines what it means for something to behave like a list, right? It has to be able to support certain operations, like I should be able to add items to it and remove items to it and get and set items at a particular position. That's what I need to do in order to be a list. There are different implementations of lists in Java. One of the more common ones that people use is called an array list. And we're going to build our own array list over the next couple lessons, and you'll see how this works. So in Java, remember, everything in Java is either a primitive type, an array of primitive types, or some type of object. An array list is a class. I create a new one, and it stores the values in the list internally in an array. In fact, let's see here. Let's see if we can find the implementation of the array list class somewhere. Oh, here we go. Okay. Blow this up a little bit. So here's my array list. This is Javadoc for it. And it's empty data. Here we go. So internally, the array list class stores the object references inside of it in an array. So there it is, right? And then the rest of these are things like different ways to create it. And I'm sure we can find, let's see, there's the size method, right? just returns the size, which is maintained, I guess, as a private variable. Anyway, so there's code that implements this, and this particular implementation of a list uses an array internally. Now, arrays in Java are fixed size. And so one of the tricks, which we'll come back to tomorrow about building a list on top of an array in Java, is that you're going to have to deal with changes to the list size. So that's the difference between a list and an array. A list is also an ordered data structure, just like an array. The metadata that it adds is that it associates a position with every item in the list. Unlike an array in Java, list sizes can change. So I can add items to a list, I can remove items to a list. It's very much like a list in certain other languages like Python, where I can create an empty list and then add a bunch of things to it and subtract them and slice it and do all sorts of cool things. Java lists have many of the same features. So let's mess around with them a little bit. What I'm going to do here is, and even just the declaration of this is interesting, right? So, and it's a good review of interfaces. So on the left, I have an interface type. This list variable can refer to anything that implements the list interface. And this is normally what you want to do when you work with the list. You can use an array list in Java directly, but sophisticated Java programmers will use the interface type. And that actually allows us to do things like later, for example, maybe I discover that the array list isn't a great fit for my application from a performance perspective. I can very easily swap out to one of Java's other list implementations. So there's also something called is it linked list? Yeah. So I have another way of implementing a list. Now it's mad about this one. So I have a couple of different list implementations that are built into Java. The performance characteristics of these differ, and you're going to understand why by Friday, because we'll have implemented chunks of both of them together, and we'll be able to look at the code, our code, side by side. So that'll be fun. So for now, though, we're just going to focus on using the ones that are built in. I'll just use an array list. Now, initially, this list is empty. I'll print off the size here, right? But unlike an array, I can, I'm not, like when you create an empty array, it's just like, why? It's empty. It's never going to be useful, right? You're just going to have to, there's nothing to do with it, right? A list, on the other hand, I can add items to. So I can say list.add. If you add an item, there are two versions of add. So I've added two integers. Now let's print the size of the list, and now let's also print the list itself. Lists have a much nicer print method built in. You'll see that the default add function adds the item to the end. So if I just call add and I pass an object, in this case what's happening is this is int literal, it's being boxed to an integer and then passed to the function. If I pass an index, I can also add things at a different position in the list. So now what you'll see is I add 10 first, that's the only item in the list, and then I add 12, but I added it position 0. And what that does is it pushes 10 back into position 1. So if I just call add, I add at the end. If I provide an index, I can add anywhere in the list I want to. So for example, I can do list.add at position 1, 8, and now what you'll see is 10, 8, 12. I had a list with items 10 and 12, and then I put 8 in the middle. I put it in position 1, meaning that 12 got scooted back to index 2, 10 was unaffected because it was still in the first position. So, Java lists, that's how they work. And you guys, will be expected to be able to use these, and they're pretty nice. Actually, the list interface is pretty useful. Now let me show you again what's nice about using a list type rather than a specific implementation is that I can then later swap this out. Well, I've got to do the import properly, and everything works. So I've got two different implementations in Java of the same data structure, the same interface, right? That work differently. They conform to the same interface. So from my perspective, they're the same. They all support add and size and remove and get and set and things like that. But internally, they're implemented totally differently. And again, we're going to understand that in a few lessons because we'll have done this ourselves. We'll see how to do it. Okay, so now the new piece of Java syntax that we're introducing here, we introduced through the sake of an example. So one thing you might have noticed here is that when we created the list, there's no type here, right? This is just a list. And it turns out I can put anything into this list. Oops, sorry. I got to put the item to add is the second argument to add, right? So now I've got a list that has a mixture of integers and strings. And if I created a new class like, right, I'll create a dog class, I could add dogs to the list. New dog. Now it's just, right? So this list can store any Java object. Now, on some level, that's extremely powerful, right? There's one list implementation that can store any kind of Java object. On another hand, there's a problem here, which is that there are times when I want to make sure, there's times when I actually need a list of objects, but there's also things that this makes kind of a pain, right? So let's say I do something like this. So at this point, I know that string s is equal to list.get. So let's have a getter that takes an index. So at this point, I know that the item at index 1 is a string. But if I try to run this, I'm going to get an error. And the error occurs because when I put things into this list, Java is upcasting them to be objects. When I get them out, what I get out is an object reference. So if I change this to object, it works fine. But now I have an object reference instead of a string reference. And I can't do things that I would want to do with the string to it, like trim it or whatever. Now, you can do this. I can do a downcast here, and that will work, right? So I could do system.out.println s.length. I've got a string. The problem is, what about if somebody came around and did this? Wait, I've got to put it in the front. Nope. Oh, wait, sorry. Now let's put the dog in position 1. Right? So now, before I get to here, let's print off the items in the list. So you'll see that the problem is that I have this mixture of different types in the list. I've got some integers, I've got a dog, I've got a string. And when I pull one out, it could be any of those, depending on the position. And so in this case, at some point, given an earlier list, what was in position 1 was a string, but now because I've added some new elements, that string is in a different position. When I pull it out and I try to downcast it, I get a class cast exception because what's in item position 1 is actually a dog. So the question becomes, how can you, normally when you use a list, you want to use it to store a certain type of thing. You don't want to use it to store any type of object. And so you want the compiler to help you in two ways. First of all, you want the compiler to help ensure that the things that go into this list are the right type. So that's one thing that the compiler will be able to check for you if you can tell it what type of object I want in my list. The other thing I need to do is when I get things out, I would like the compiler to automatically know that they're a particular type of object and do that cast for me, essentially. And the way that we do this in Java is we're using this feature that we have not seen before, and we will come back to a couple of times and discuss in more detail, which is known as a type parameter. When I create the list, I can tell Java, and I need to use this on both sides, we'll talk about that in a second, I can tell Java what I'm going to put into the list. So this says, I'm creating a list of strings. This list is going to be used to store strings. I can also put anything into this list that has an is-a relationship with the string. So if string had any descendants, which it doesn't because it's final, if it did, I could also put them into this list. Now immediately when I run this code, you're going to see it doesn't compile. And the reason is the compiler now knows that I'm using this list for strings. And so when I try to add something to it that's not a string, like an integer or a dog, it's going to point that out, and it's going to refuse to compile. So I'll change these to be some new things. So now everything I put into this has to be a string. And now it works fine. And now the other thing you'll notice is I don't need this, this downcast anymore. What comes out of the list when I call list.get is also a string. And so this is typically how we use lists and other container data types in Java. So what we've been using up until this point without the type parameter is sometimes known as a bare list. And if you try to use this in an IDE, you'll typically get error messages saying that you should provide a type. The reason to provide this type parameter is because it allows the compiler to check things for you. And it also simplifies your code when you're pulling items out of the list. Because now I know that everything in this list is something that I can safely refer to as a string. When I use this, let's see what happens if I do this. That also seems to work. Usually what you want to do is you want to apply the type parameter to both the implementation and to the reference. I can do this over here. That will also work. So basically this says create a linked list that can hold strings and refer to it using a list interface variable that I'm going to use to refer to strings, to a list of strings. But usually the type parameter on the right side of my initialization when I'm using a parameterized class matches the type parameter on the left side. And if I want to just copy the left one over to the right, if I use this empty diamond, right? So it's like where I would put the type parameter and I just leave it empty, Java will do the right thing. So, and so this is a new piece of syntax for us to use, and it is something that we will use when we're using lists. And eventually we'll look at how to build classes that use this feature, because this is actually a really neat feature of Java that we'll get to later in the semester. For now, when you start using lists and maps and other built-in Java data structures on the MP, you're going to see these type parameters, and so I wanted to make sure that these were something that people were exposed to. So we saw them today. All right, so I'm pretty much out of topics to cover on today's lesson. Please go through, you know, the walkthroughs and stuff like that. At this point, I'm happy to take questions on lesson content. We could also look at parts of the MP if people would rather do that. I'm here and available for another 20 minutes, half an hour. So fire away, and we'll address, you know, whatever sort of concerns you have on the MP. Or on the lesson, or whatever. Life, you know, whatever you guys are curious about hearing about today, go ahead and put it in the chat, and we'll address it. It seems like people are off to a pretty good start on the MP, which I'm happy about, obviously. If you're running into problems getting things set up, I mean, please do come talk to us, join up the help site, find us on the forum. I mean, this is really the time to get that stuff nailed down. The first MP checkpoint is sort of intentionally not super heavy in terms of amount of code you have to write. And that's really to provide time for, you know, the types of things that come up early on when you're getting started, right? Problems installing stuff, problems configuring, you know, whatever. Those things kind of, those go with the territory. And so, but, you know, the sooner that we can find, you know, the sooner we can get to you, right? The sooner that we can start helping you with some of these things. And some of them take time to set up. The nice thing about it is, you know, once you have the MP working, and Android Studio set up, and you've, you know, finished whatever sort of initial startup tasks need to be accomplished, then you don't have to do that next time. Everything's all set up, ready to go. In the future, it'll be a lot simpler getting off the ground. But this is the point in which we have to address some of these, you know, startup things. Yeah, I'm happy to talk more about the MP. I'm happy to answer any questions that you might have about it if you have questions. like I said, happy to discuss the MP, but you got to give me a starting point, right? I'm not just going to vamp on it. So you have a question. So happily, it looks like we had a handful of students that had already finished the first MP checkpoint, which is pretty impressive. Also a handful of reasonable number of students that are making progress towards the checkpoint. It looks like a reasonable number that have finished up. Let's see here. That have finished up at least the first bit. Yeah. Let me switch the view here. Let me fire up Android Studio. Let's see here. All right, let me go pull up Android Studio. Let's see here. Android Studio, sweet. Okay. Yeah, so let's pull up. So let's look at the server first. So the idea here is that there are what you're really building for this MP is an entire system that would eventually operate over the internet. So normally, again, I think I did a little bit of this last time. Oh, I can't switch away from here as easily. So the question would be, where would information about courses at the university be located? What we've done right now is we've given you in a file, right? So for example, this file, this JSON file that's included in your repository has information about all the CS courses for fall 2020. But normally what we do when we build an app like this is that information isn't part of the app. It's retrieved across the internet. So when the app starts up, it might say, okay, the user has configured me to look for courses fall 2020. So I ask a server that's located somewhere else on the internet, hey, can you send me all the information you have about fall 2020 courses? And so essentially what we were doing is we're communicating across the internet, right? There's this, and you can really, one of the reasons why we talk about serialization is you can really think about this as me being able to send strings back and forth, right? I can't send a Java object over the internet. I can send a string. So when I ask the server for some information, what it responds with is a string. And then I need a way to interpret that string so that I can pull the data out of it. So there's a couple of steps that are required here. The first thing is I need to have a server to talk to. What we've done for this particular MP is we've embedded the server inside your app. Now again, this is not a normal thing to do. Normally the server would be located on some other machine. You would run it in the cloud, or you would get access to a server on campus and run it there, or whatever. For this MP, the server is actually located within your project, and the reason for that is you get a chance to look at it and understand a little bit about how it works, and you're actually going to modify it for later MP checkpoints and have it do some new things. The server, hold on a sec, I do need to figure out this because I need to be able to. Well, it looks like I can do it. Just do that. So, okay, so let's look at So here's an example of a existing web API that I'm able to access even just through my browser. So the server that I'm accessing is called courses.illinois.edu. I have no idea where this is, but I suspect there's some machine on campus that is this server. So when I'm talking to it, my browser right here is communicating with that machine across the internet. The request, the way that you typically make a request to a server like this, one of the pieces of information you provide is this path. So you break up the request into a couple of different parts. This is the name of the server, and then what follows here is this path. And the path is used by the server to figure out what to send me. Now you notice if I do things like this, I don't get a good response back because the path is incorrect. So in this case, it's important that I have this .xml because that's actually telling the server what kind of document I want. So now how this path is interpreted is completely up to the server. Whoever programmed this made a decision that the URL should look like this. So in this case, every one of these starts with sysapp, Explorer, I think that's course information system or course information service, Explorer/schedule. And then so that's actually true of most requests to the server. But then this next three parts, I have a year, a semester, a course, department, and then a number. And so those are sufficient to identify a particular course that I want information about. Now, if I put in like something like this, then I get this not found error, right? Because I'm asking for a department that doesn't exist. If I misformat this request, so maybe I do something like this, right? CS, same thing. I've now given it a request it doesn't really understand. So I have to agree, the server and I have to agree on the format of this request. And the information that I provide has to be correct. If I ask about a year that it doesn't have, I get the same thing. So this is really a form of an interface. There's a contract here that I'm agreeing to as the client, and if I don't meet the requirements of the contract, I don't get a good reply. But if I construct this URL properly with all the information in the right place, I can get back some data. And this is pretty interesting. I mean, this is basically, a lot of information about this particular course. So the number of credit hours is shown. There's information about the prerequisites. Does it meet any gen ed requirements? That's in here too. And then it has links to all the different sections of the course. If I look at one of these section links, so let's look at this one, right? So this one, you'll see some of the same pieces. So it's the same server. I have sysapp, Explorer schedule, 2020 spring CS. But now, instead of cs125.xml, I actually have this additional component. This is the CRN. This is a course registration number. This is what you actually use to sign up for the class. And then .xml. And now in here you see, and this is information about this specific instance of this specific section. So this was last semester. I'm looking at spring. It has the days of the week. We met on Monday, Wednesday, Friday, 10 to 11. That was in Lincoln Hall Theater back when we were still in a building, right? So this has more information about that specific section. Okay, so this is an example of a web API. What you guys are running here as part of your project, you're actually running your own server, and you actually are going to be able to set up your own paths and your own routes and return data in your own format. So what happens here is that when I request a particular path, and in this case I have to request /summary /year/semester. So I borrowed some of the same format from the actual official courses backend API. You end up in this piece of code. And what this piece of code does is this is stuff that's checking to make sure that the summary is formatted properly. And you guys we're gonna talk about maps quite soon, right? But what it does is it looks up this information in a map. If it has information about that particular course, then it returns that as a string. So that's your server. Now, right now, this server runs alongside the rest of your app. But if you were going to deploy this, what we would do is we would take this code and we would probably rewrite it a little bit because we would use like kind of a different library to do it. And we would run it on some computer. And we would have to set up like a name for that computer and stuff like that. And we would deploy it somewhere. And then we would have this app talk to that computer instead of talking to this local server. And really the only thing we would have to change, if you look at our application class, this is the URL that's being used to contact the local server. And this URL, localhost, is a special host name that means connect to that machine. to the same machine that I'm running on. And then we're using this port number, and we'll talk a little bit more about some of these things later on. But this tells the app where to find the server. In this case, the server is running on the same machine. If I wanted to run it somewhere else, I could do something that like set this to be courses.illinois.edu, and then the server port, and this would all work as long as I stick to the same agreement about how to request various pieces of information. So that's the server. The client, so the server is an unusual part of your MP. That's not something that a normal app would have. We've given it to you, and we're going to expect you to modify it so that you understand things a little bit more in more detail, right? In the past, what we did is we set up a server for you to use that was located somewhere else, but then you never saw that code and you didn't really understand how it worked. And I think this will give you more of an understanding about the full stack of this application. The client is a part of your app that's responsible for communicating with the server. So the client's job is to make the requests to the server. So when the main activity loads up, in order to render the UI, it needs a list of courses to display. And so what it does is it calls this method, and we could have called this something else. Maybe it should be called get summaries or get summaries for your semester or whatever. It calls this method. It tells it the year and semester that it wants summaries for. And it provides, and this is important, this is a callback, it provides a way for this function to return the data once the request is complete. This method makes the request. When the request completes, so when I make this request, this is using a built-in Android library for making HTTP requests. It's called Volley. And then we'll talk, in future, in MP1, the next checkpoint, we'll go into a little bit more detail about this because you guys will be modifying some of this code and adding some of it. So what I'm doing here, this is just a new object I'm creating. This is a request. This tells Volley what I want, right? In order to make this type of request, I have to tell it the URL to use. So I've constructed that from that server URL that we just looked at. And then summary plus the years plus the semester. So this is going to be a URL. In our case, it's going to look like http://localhost:8888, that's the port, /summary/2020/fall, right? Or /2020/spring. The only semester that we have data for right now is fall 2020. This says this is a particular method to use. This basically is a method to be used to retrieve information called a GET request. I tell it the URL to use. And then there are two Lambda functions here, which is kind of cool because we just talked about those. These are Lambda expressions. These methods are called when the request is finished. And there are two of them because it's possible the request succeeded, or it's also possible that it failed. The second one is used if it failed. And here what we do is we just log the error message. If it succeeded, what happens is what we expect to receive back from the server is JSON that contains that list of course summaries. We used Jackson. This object mapper is imported from Jackson. So this is something that you guys used before on one of the homework problems. We use Jackson to deserialize that string into an array of course summaries. And then now we have data that we can return to the code that made the original request. And so we use the callback to do that. So we say callbacks.summaryResponse. This is an interface that's defined right here as part of this class. And it says, the summary response method by default does nothing, but you'll look at, if I go here, go into my main activity, the main activity has implemented or overridden that and uses it to update the list of courses. So every time this app starts up, the following thing happens. The first thing that happens is it starts a server. So now I have a server running that's actually waiting for requests. The main activity fires up. You'll see in its onCreate method, it calls getSummary. And it passes that default year, which is defined to be 2020, and the default semester, which is defined to be fall. So it's saying, I need data about the courses for fall 2020. The client, which we were just looking at, then uses the URL that's configured on the application and this path that we've agreed on with the server, and then asks the server for that data. The next thing that happens is the server receives this request. It uses the path to figure out what to do with it. It says, okay, well, this starts with summary, therefore this is a request for summary information. It hands it off to this method. That method checks to make sure the request is formatted properly, sees if it has information about that particular course year and semester. If it doesn't, it returns a not found response. Otherwise, it returns an HTTP OK, which means I was able to handle this request, and it sets as a body for the method a string that contains all of that data. So main activity starts up, tells the client, I need summaries. The client makes the request to the server. Server responds. Now we're going back up the stack. So this is a full stack web application from the UI to the client all the way down to the server. Server has the data, returns to the client. The client runs this code to deserialize the request to an array of summaries. So now I know what courses I'm going to display. I use the callback that was registered by the main activity to return that information. The main activity has implemented this callback so that it replaces that list of array of courses. It's a list, actually. Yeah. So here's the use of a list right here. I replace the list. The arrays has a utility method that will convert an array to a list, which I use. And then this line of code is what replaces. So currently the list is empty. The list of courses that are in the view is empty. This, what it does is it starts an edit. It says replace all. So basically it says replace all the courses that are visible with this list. And then this .commit causes the changes to be visible. And so that's what happens between the time your app starts and the time the courses are actually visible in the display. Main application starts, uses the client to make a request to the server. Server responds. Client passes the data back to the main activity. Main activity uses this method to replace the contents of that visible list with the data that came back from the server eventually. So for now, if you look at it right now, essentially there's only one method that you can call on the server, which is this get this summary information. This is a method that is here for testing, and we can talk about more about what this is, but this is just a very, very simple method that just allows the test code to make sure that the server is online. In the future, so for the next checkpoint of the MP, what you're going to do is you're going to build a view that allows me to look at details about a particular course. So currently I can see the list of courses, but what I want to happen is when I click on one of those courses, I should see more information about it. I should see a screen with like the title and the full description and maybe some other information. To do that, you're actually going to add code to the server and to the client, because the server now is going to be able to return information about a specific course. So right now I'm asking for information about an entire semester. Next time you'll be actually able to, you'll add code to ask for information about a specific course. So you'll say, hey, give me all the detailed information about this class. That's why we've given you this file. So if you compare these, this file only has the year, semester, department, number, and title. It actually has a description. I might get rid of that for the next MP because it's sort of a mistake on my part. This file, on the other hand, has all, if we go back and look at this, let's see here. Yeah, it has all the information here. It has a label, it has credit hours, it has course section information. You can see all of that information is available in the JSON. And so some of this is stuff that you'll have to display in order to complete the next part of the MP. So yeah, so this is, and again, this is a, let's see here. Why is it typeless? Yeah, I'll come back to that. The binding part. The binding is actually a thing that's for the UI. That's the so the callbacks are tricky, right? The reason we use callbacks is we can't return information directly, right? Essentially, I need to be able to so if you look at the way the client code works, it builds this response and then it adds it to a queue. And what this networking library will do is that at some point later, it'll execute this request and then return the result. And so what I do is I provide a callback as part of the request, and then that callback actually uses the callback that was provided to the method. So there's actually two levels of callbacks here. The best thing I can do about callbacks is send you back to that video about them and have you go through that again, and then maybe ask some questions on the forum, and maybe we'll put together some more information about this for the right after the next part of the MP. Yeah, good question. Let me get to that last question before we wrap up today. I gotta get to my other view here. Oh, crap. I'm so sorry. I thought I was showing you guys parts of the MP, but I was showing you parts of... Okay, well, that was bad. Someone should have said something about that. Oh, well. Okay. Let me go back here, and let's go back to our example. Where'd it go? Yeah, so the question is, and why is this of type list? By making this of type list, it doesn't tie me to a specific implementation. So if I make this of type array list, then if I want to, so right now, for example, let's try this, right? So let's say, make this array list, strings, new array list. That works fine, right? And this will work completely well, right? Except that, what if I want to use a linked list, right? Which is a different list implementation. There are more than one list in Java. So now if I do this, now it's mad about the array list, and if I import array list, what you're going to see is it's going to complain about casting, right? It basically can't figure out how to do this, and there's all sorts of other things that will go wrong here. I know people have seen this in high school, but it's wrong. It's just wrong. So we will never use an array list reference type for something that's a list. The whole idea here is that the reference is something that behaves like a list. How it's implemented is irrelevant. Whether it's an array list, a linked list, there's like a hash set list, there's a bunch of other different list implementations. Here, this is only a small problem, and I could fix it by just changing both pieces of code. But when I write functions or methods, they always return lists and take lists as parameters. Because I don't really care if it's an array list or not. Now, if you have something that really needs something to be an array list, then you might have to do that, but there's not very many cases where that's true. Normally, what you care is that it behaves like a list, right? It has an add, a remove, a set, a get, and has all the methods that every list has. How it's implemented is not important. And so again, I know people see I think the problem is in high school they don't want to talk about interfaces or something, and so they use an implementation type for the reference, but it's wrong. There's no real reason to do that, and it causes your code to be less general. So again, let's say I have a method. Let's call this public. It doesn't need to be public, does it? So I'll say array list filter array list, and I do something in here, right? I'm not going to implement this, but you could implement this as a method. Now the problem is I can only call this using array lists. But why, right? The code in here is not going to use any special features of an array list. And so now if I make this more general and I just allow it to take any list as a parameter, return any list, now I can pass any list I want to it, right? And so the idea behind these interfaces, and this is true the same thing of map, which we'll talk about, just like a dictionary in Java. All the different Java collection types have interfaces associated with them, and you should use them as much as you can. You obviously can't use it on the right side. On the right side of the assignment, you need something that implements the list interface. And so there's where you choose an array list or a linked list or whatever. But it's the number of times where you actually want a reference variable that has an array list type is very small, and it's usually wrong. So it's just a good habit to get into to avoid that pattern. We don't care that the reference is an array list. We care that it's a list, something that implements a list interface. And by writing methods that take lists as parameters and in general avoiding the use of array list or linked list reference types, you'll make your code a lot more general, and it's just much more idiomatic, right? I mean, when people use array lists for variables, typically it's just a sign that they haven't they haven't written a lot of Java code, or they haven't been in a situation where they've been around people that have understood interfaces and how they're used. I know this is an idiom that comes out of, I think, high school Java classes that do this, but yeah, it's just not the best way. All right. Yeah, good. All right, I'm out of time today. Tomorrow we will continue with lists. So basically over the rest of the week, we're going to do 2 implementations of lists. Tomorrow we'll really dig into array lists, and we'll implement some of the cool parts of those. And we'll continue to talk about algorithm analysis and use some opportunities to do that, and practice with built-in Java lists. And then on Thursday, you guys will actually implement a linked list, which is a really neat alternative that uses linkage to link items together rather than an array to store items has different performance trade-offs. And so those are fun to talk about. And then on Friday, we'll basically kind of come back and look at the two side by side and talk about kind of some of the trade-offs that we've identified and things like that. So should be fun. I will be back tomorrow. I will see you guys then.